Today we have with us Abhilash Sreekumar, who is a researcher at the University of Nottingham. Let me just read out his bio for you so that you get more context. He's a graduate of MSc Computational Sciences in Engineering at TU Braunschweig, Germany. He specialized in numerical and simulation methods in solid mechanics. Currently, he is a Marie Curie Fellow pursuing a PhD in mechanical engineering at the University of Nottingham. He carries out research in developing novel numerical methods for simulating mechanical and vibroacoustic phenomenon in porous media. There's more to it because he's doing a lot of work, but I will let him tell you about the work he does. With that said, Abhilash, over to you. Thank you so much for agreeing to do this session. I hope this will be a good use of time for everyone. Over to you, Abhilash. Thank you.
Perfect. Thanks very much, Imad, for that nice introduction, and thank you for giving me the chance to speak about this. I just realized how cluttered my entire approach to all this was, so this helped me narrow down and focus on what I really want to say. I'm assuming that everyone can hear me at the moment. If anyone cannot, please do let me know. I can stop and figure out what's going on. Firstly, thanks to everyone for joining us on this Saturday. I mean, it is holidays and I didn't expect many people to be interested, but it turns out there are quite a few. So yeah, thanks for that. I hope it will be a nice presentation. I've got a couple of things lined up. Most of you, as I understand it, are from a data science background. So of course, you'll be understanding quite clearly what PCA is, principal component analysis. Maybe I can give you a fresh perspective as to how I use it within the context of computational solid mechanics, numerical methods, and so on. As a disclaimer, I am not a computational data scientist. I am a computational mech guy, but I don't work on the data science side of things. It just happens that the techniques that we use, such as linear algebra, statistics, probability, and maybe a little bit of calculus and so on, they are common with the data science community as well. So anyway, without delaying this much further, let's get into it. I think you will enjoy this. All right, this is how the presentation is structured. We've got the motivation and background where I talk about why we are going to be doing what we're doing. Try to motivate it in a way that somebody who's not too familiar with this topic can also follow. Next, we move on to the classical linear algebra refresher. I know everybody's done this 100 times and I'll do it the 101th time very quickly just to get it out of the way. Next, we talk about the meat of the presentation, which is the proper orthogonal decomposition. This is just a fancy term we use in mechanical engineering and certain applications like this, but it has at its heart the PCA and maybe singular value decomposition as well. So it's basically PCA parading around in disguise, so to speak. Next, well, I can assure you by the end of this, there might be a little too much mathematics. I hope that is not the case, but it might just happen. So to clear everything up, I implement the algorithm live in front of you on, well, I do it on MATLAB, but it can be done on Python as well. I apply this to a simple problem and then a real world problem and see what results turn out. And I can assure you the results will be quite interesting. It might even generate controversy because the first time I saw it, I was blown away. It was mind blown. How can something be this effective? But as with everything, we can see that there is no such thing as a free lunch. There are several limitations, places where you can and cannot use this. I speak about this in limitations. Finally, we move on to summarize what we've looked at and conclude. All right, this is how we plan to do this. So now let's begin. Of course, as a general comment in the middle, anyone is free to ask questions here. As Imad has already mentioned, I will answer the questions anywhere in between or at the end, as you like, really, it doesn't matter. And no question is a stupid question, please ask away. All right. To simplify things, let us consider two scenarios. An idealized high school physics project here, which is basically a pendulum. And I just realized I don't have my laser pointer on, and now it's on. All right. So we've got a high school physics project here, which has a pendulum oscillating. In mechanics, we call this a harmonic oscillator. And on the other hand, we have a real life application, for instance, a civil engineer in Japan who has to design a building like this. I picked Japan in particular because all of you know the challenges that a Japanese civil engineering or a structural engineer would face, which is developing earthquake-resistant buildings. You know this, right? Because Japan is based on a fault line, and they receive quite a few earthquakes per year, and so on. Anyway, let's say the problem is, how does each system respond to a type of excitation? For the high school physics project, we consider a simple example, such as a baby playing with a pendulum. It's a silly example, but you will see quickly how complicated it gets. For the civil engineer in Japan, we have a more realistic scenario, which is how the building responds to earthquakes. There are several ways to approach this problem, and we'll investigate them one by one. The first approach is the classical, the cornerstone of all natural science, which is experiments, right? Of course, there are mathematical models and so on, but no mathematical model, despite how consistent and coherent it can be, will be considered valid if it does not correspond to fact. Ultimately, science is empirical in nature. So we carry out the first tried and tested approach, which is the experimental approach. To do this, we identify all possible cases that might occur. Let's maybe brainstorm and think of a few things that the baby can do with the pendulum. Number one, for example, it can push the bob vertically, or something like this. Another option, it can release the bob from a height. It can hit the ball radially. That means give it a sort of a radial or a tangential excitation so that it revolves like a gyroscope, for example. Or another option, a 1001th option, after listening, we might end up with another possibility, which is it can twist the bob and string. As you can see, there are quite a few things that the baby can do with the pendulum, and it is our job as an experimental scientist to list out all these possibilities. Similarly, what would the civil engineer do? He would have to narrow down on several excitation scenarios. By excitation here, I mean different types of loading, different types of phenomena that can occur to disrupt the building. For example, the first one could be violent shaking. We could have ground cracking and splitting. We could have tsunamis induced by the earthquake, and so on. We can list several items, and another example would be soil softening and collapsing, for instance. Right? What do we do next after identifying all these cases? Well, within a controlled scientific environment, we measure, record, and test. This is the experimental approach for you in a nutshell. Let us examine the benefits and drawbacks of this experimental approach. Of course, when doing it for the case of a baby, it is very simple. All you need is a pendulum and, a baby. Even if you don't have a baby, you can just do it yourself. So it's cheap to do. However, doing it for a building in the real life scenario is, quite expensive, isn't it? You, of course, cannot do it to a real building. What you need to do is create models. Creating a model and simulating all these different types of excitations can be extremely expensive. Next, as far as time is concerned, even the simple case of a baby playing with a pendulum can take a lot of time. Why? Because you have to simulate 1001 cases. Needless to say, the same case with the real life simulation, that is the earthquake as well. As far as skills are concerned, you don't really need too many skills, do you? You just need to know how to operate a stopwatch, and that's about it really. Whereas for a civil engineer, yes, there are several skills involved, and I don't need to go into it. I think you can figure this out yourself. Finally, the hazards involved in simulating a baby playing with a pendulum is nothing. Right? There's nothing that can really go wrong, that can be life-threatening. Whereas what happens if you go wrong with a civil engineer? The building collapses. That's what happens. So it's quite dangerous. So as you can see, the experimental approach, it is good, but it has its limitations. There is the next approach, which is a mathematical modeling approach. This is a slightly different approach, which is based more on analytic deduction rather than experiments. All of maths and physics can be captured through ordinary or partial differential equations, right? For example, this equation that you see here is the classical equation for wave propagation. Another example here, the building amidst an earthquake. This is the classical example of a vibration equation. If you look at both these equations, it will turn out that solving them exactly is impossible. Analytic solutions rarely exist. Alternatively, there are other procedures to solve these equations. These involve numerical approximation techniques, such as finite differences, finite elements, and so on. These involve approximating these equations with a set of linear algebraic equations, which make it a lot easier to solve. The advantages of this approach is that all you need is a good computer, so it's quite cheap. That's about it. As far as time is concerned, let us look at the baby playing with a pendulum. We can simulate this quite easily. This is a simulation I did. It is called a damped harmonic oscillator. What you can see here is the mapped trajectory of a pendulum that is released from a height. You just let it go, it swings, and damps out, and eventually comes to rest. Right? It's quite straightforward. The interesting thing here is that the time taken to simulate a single case is 0.4 seconds, right here, quite simple. However, as we mentioned, it takes around 1,000 different cases exist, isn't it? So for these different 1,000 cases, turns out it takes around 6.7 minutes, which is quite expensive in my opinion. In the case of an earthquake simulation, as you can see, this is a structural optimization simulation that I've done recently. Even a single iteration takes 242 seconds. To simulate the problem for 1,000 different cases, it will of course take 2.5 days or 2.8 days. So bottom line, it is very expensive to do. Next, the skills involved in simulating a damped harmonic oscillator is quite, well, it's nothing really. Right? All you need to do is a bit of mathematics and that's about it. Whereas, yes, to simulate a structure like this in the real world, it is quite complicated. So it still requires a bit of skill. The good news is that the hazards involved in these type of mathematical simulations are little to nothing. Right? Nothing. What can happen when you're working at a computer except computer crashing? Let's move on to another approach called the meta-modeling approach, which seeks to address some of the limitations of this previous technique. The previous technique being mathematical modeling. Right? So meta-modeling happens exclusively on computers. You've got a baby playing with a pendulum. For that, a solution can be formulated like this. And this is an intuitive solution which you can borrow from analytic solutions if they exist. To be honest, in this case, this is in fact the analytic solution. The advantage with this is that you don't have to resort to numerical techniques. You can exactly predict deterministically the response of the system at any instance of time, at any phase, at any distance. Whereas in the case of a building amidst an earthquake, there exists no such intuitive model. We need to go for a more sophisticated approach, which is in this case a data-driven approach. The advantage of a data-driven approach, as you can see, is that the hazards are reduced. It does not require any skill. The user just needs to treat the model like a black box, plug in his input, and out comes the output. Very simple. There are, well, it's very cheap to perform. It doesn't cost much. It doesn't take too much time either. So it's very simple, really. Let's move a little more into data-driven models. This talks about what exactly is going on. With any system, we begin with an input excitation. We pass it into a model. To explain what is happening, I juxtapose a mathematical model alongside a meta model. For the mathematical model, we've got, well, it's physics driven. It captures the physics of the system. And out comes the response. Of course, we also use the data generated by the mathematical model as a feedback mechanism. We use this as training data for the meta models. So the question is that for meta models, where do we get the data? The answer for that is through approaches, through either the experimental approach or through this mathematical approach. So we generate a lot of training data through the mathematical model and give it to the meta model and so on. As you've already seen, generating this training data basically means you need to generate a series of high fidelity, accurate results, right? Generating them with the mathematical model can be very expensive. We shall see that in a moment. And as a result, training the meta model offline, I mean, let's be honest, it happens offline, can be very slow. In the case of a mathematical model, as you've seen already, there is no question of training involved. All you need to do is plug in an input and out comes the output. Whereas in the case of meta models, you also need to train it, as I've mentioned already. The online procedure, when solving it, the mathematical model takes a lot of time, whereas the artificial intelligence-based model, that is the meta model, is very quick. This is the trade-off. That is, the offline procedure for a meta model can be a little slow, but when you're actually using it live, it can be very expensive. The issue is that, as always, in the case of meta models, we encounter the curse of dimensionality. That is, a huge training set is required, and generating this huge training set can be very expensive. The question now is there a cheaper way to generate this training data? The answer is yes, of course we can. With this, I hope I have sufficiently motivated what is going on. Let us move to the linear algebra refresher very quickly. All right. It won't be much, I promise you. It'll just get the terminologies out of the way. First, let us look at what the dimension and basis of a space means. The basis of a vector space is a set of linearly independent vectors. What is a vector space? Well, it's very simple. It is a space containing vectors. I know it seems like the chicken egg story, but that's what it is. So this is an example of a vector space. This is an R3, an Euclidean space, where you've got x1, x2, and x3. This is a physical space as well. This is spanned by the bases E1, E2, and E3. We'll see what it is in a moment. As it is quite evident to you already, the number of elements in the basis here being E1, E2, E3, corresponds to the dimensionality of the space, which is n. For this example, it is a three-dimensional space. The natural basis for this problem is very classical. It's E1, E2, and E3. These are your general I, J, K vectors, if you remember your vector algebra, right? Quite simple, quite straightforward. Let's move on. There also exists another special basis, so to speak. This basis is dependent on the operator being performed. I do not show the operator here, but let's just assume for the sake of argument that this qualifies as another basis. This is called an eigenbasis because it satisfies a set of properties. All right, we'll get to that in a minute. Let us understand the notion of spanning very quickly. Spanning basically means that any member of this space can be expressed as a linear combination of the basis vectors. By this I mean, let us consider an arbitrary vector here. For example, 5, -4, 10. This is an example. As you can see, we can express it as a linear combination of these basis vectors. That is 5 times E1 minus 4 E2 plus 10 E3. You can try it out and the mathematics just works out. It's quite obvious. The same thing can be done with this eigenbasis as well. 4v1 times minus 2v2 plus 1v3 and so on. Quite straightforward stuff. The important thing to note about a basis is that it needs to be linearly independent. I mentioned this here in italics and it is absolutely critical. All right, let's move on. Let's understand the notions of scalar product and further what orthogonality means. The scalar product is something all of you might have seen at some point. You must have learned it as a dot product or as an inner product, for example. Here we represent it with two, whatever these kind of brackets are called, I forget, oblique brackets, for example. It is defined mathematically as follows. The scalar product of two vectors, that is A and B, is defined as follows. It is just the summation over the entire dimension of the product of its corresponding indices, where V, this fancy V here, talks about a vector space. An example here, we've got two vectors, 1, 2, -4 and -2, 7, 3. For this, the scalar product is as follows. I mean, we just follow the definition, quite clear. I picked this example to show you something interesting, that the scalar product of these two guys here is 0. Whenever this happens, we understand that these two vectors are orthogonal to each other. That is, they are perpendicular to each other, right? That is the definition here. A and B are orthogonal to each other if and only if the scalar product of both equals 0. Now, as you can already imagine, by orthogonality, what we mean is, that the vectors A and B are independent of each other. So obviously, orthogonality implies linear independence. But we must be careful that the reverse is not true. Linear independence does not imply orthogonality. To show you an example, let us consider the basis vectors we just spoke about, E1, E2, E3, V1, V2, V3. Both of them are linearly independent. That is, you cannot express one in terms of the other. However, only E1, E2, and E3 are orthogonal to each other, or in this case, orthonormal. The word orthonormal is just a fancy single addition to the term orthogonal. It just means that the two vectors in the scalar product are orthogonal to each other and they are normalized. That is, the magnitude of each vector equals 1, basically. This is written in fancy mathematical notation as follows. EI, the scalar product of two vectors, EI and EJ, is the Dirac delta function delta ij, which is defined very simply, which is equal to 1 if I equals j and 0 otherwise. By this, all I mean is the scalar product of E1 times E2 always is 0 because they're orthogonal to each other. Very simple, quite straightforward. Let's move on. This is perhaps the single most important notion in linear algebra, if you ask me, eigenvalue decomposition. Let's get into it. For a tensor operator A here, like this is, by the way, the operator which I have not mentioned earlier, but I mentioned this now. The question is, are there special vectors such that when you operate on this so-called special vector, that is A times V, you end up only scaling it? That is, there is no translation, there is no rotation, there is no, well, these are the only two operations possible really. Nothing of that is involved, only scaling is involved. Yes, the answer is that is true. We can find such vectors, and it's easily computable through this. The determinant of A minus lambda I equals 0, where lambda are your eigenvalues and V are your eigenvectors. These vectors V and the values lambda are special to us because there are no rotations or translations involved. Now you might ask me, what's so special about rotations or translations? Why can't I have them? Why do I need to find special vectors that are only scalable? The reason is, well, this is the basis of all principal component analysis, really. The reason is that these vectors V, or your eigenvectors, are your stationary or minimum energy states. There are ways to justify this mathematically, but I'm not going to go through that at the moment. For example, these are the vectors we already took a look at, V1, V2, V3. These are the eigenvectors. It turns out they are linearly independent, although they might not be orthogonal. And indeed, in this case, the eigenbases, which are stored in a tensor V, as follows, are not orthonormal or orthogonal. That is, if you take a scalar product of any of these two guys, you will not end up with delta ij. Right? However, they can be orthogonalized if you do need it using several algorithms, such as the Gram-Schmidt orthogonalization algorithm, for instance. There is another condition that this eigenbasis can be orthonormal, but only if A is Hermitian. What do I mean by A is Hermitian? Well, it just means that A equals the complex conjugate of A. In this case, when we have a real valued tensor operator, this just means that it is a symmetric matrix. That's it. That's all you need to know. Symmetric and positive definite. That's just a bunch of fancy sounding mathematical terms. Don't worry about it. Now, a final notion of eigenvalue decomposition. It is always useful in certain contexts to change the coordinate system of this tensor operator from the natural basis, which is E1, E2, E3, to the eigenbasis spanned by V1, V2, and V3. To do this, well, this is the operation that we use, V inverse A, V, where V is a tensor of eigenbases. When we do that, we end up with a diagonalized matrix like this, which has along its diagonal all the eigenvalues, lambda 1, lambda 2, and lambda 3 here. Q is, like I mentioned already, it is the diagonalized matrix. In the notion of stochastics and statistics, it is also known as a decorrelated matrix, and it can also be known as the covariance or correlation tensor. We'll see how all of this works in just a minute. This, you will see very soon, is a very useful notation and is basically the crux of our principal component analysis. Perfect. We are done with the linear algebra refresher. Now let us move into the meat and potatoes of this presentation, which is the proper orthogonal decomposition. I will motivate this and introduce this very quickly. We have a variable here, which is z, a function of x, that is the displacement and time. This is because most physical phenomena as we know it are a function of the position and the time, right? And x, I should say, is better say it corresponds to the position. T corresponds to the time. X is in bold because it's a vector, and t is, of course, temporal. Now you can see that this is a continuous variable. That is, it belongs to an infinite dimensional space. It is impossible in numerics to deal with infinite dimensional spaces. So what we do is perform a finite dimensional approximation. That is, we project this continuous function onto a finite dimensional space and obtain a finite dimensional approximation called z of h. It's as follows. And this finite dimensional space is spanned by a set of basis vectors phi I of x. In this context, for the mathematics to work out, we require the basis functions to be orthonormal. Remember that this is not a necessity, it is just something we impose on the basis functions. The only thing the basis functions need to be is linearly independent. But in this case, we also require them to be orthogonal or orthonormal in this case. So what we do is that we can approximate this finite dimensional function as a linear combination of the basis functions, as we've already spoken about. And the coefficients of this linear expansion are ai of t. This is an n-dimensional space, therefore we sum it from I equals 1 to n. I have smuggled in an implicit assumption here without mentioning it, which is a variable separation. That is, you can see that z of h is a function of both the position and the time, whereas here I've split the variable dependencies. That is, the basis functions depend only on the position, and the scalars here depend only on time. But don't worry, this is quite a standard approximation. You can find it all across physics and mechanical engineering. Of course, this is quite obvious. This is the notion of convergence, which is in your finite dimensional approximation, the larger your space is, that is, if you belong to a higher dimensional space, it is obvious that you will be closer to the exact solution, right? That's quite clear. Before moving there, of course, one final thing I would like to mention here is, so for us to obtain a very accurate solution with z of h, we need n to be as large as we can. And this is where the solutions become very expensive. These z or z of h's are obtained from solving certain mathematical models, which are basically partial differential equations. And solving them at such a high dimension can be very expensive. This is where our reduced order modeling will come in, which I talk about in the next slide. We've already defined notions of orthogonality. Let us define them for a functional space here as well. The scalar product of two functions, phi I and phi j, is defined as follows. It is the integral over a domain of both functions, and this is equal to the Dirac delta function. If you remember, this is exactly the same as the notion we've described before. The only difference being that the notion before was defined for a discrete problem, whereas this is defined for a continuous problem. The way I like to think of it is that the discrete and the continuous problem are interchangeable. The only difference is a sigma sign versus an integral sign. That's about it, really. Now, if for people who are familiar with signal processing, acoustics, maybe neural networks where convolution happens, you might find that this integral is quite familiar. It looks, yeah, it is. And I can tell you that it is very familiar. I'll talk about it in a second. Using this, the associated coefficients can also be computed because of the orthonormality of the basis functions. And if you've seen, for example, I like to think of it in the form of Fourier bases. So phi I and phi j are orthogonal to each other, and we've got a couple of options here for phi, which are the orthonormal basis functions. As usual, we can take the Fourier terms. That is, we've got cosinus and sinus terms. That's obvious to us. Another example is a set of orthogonal polynomials here, like the Legendre polynomials, Laguerre polynomials, Chebyshev polynomials. These are different analytic options that we've got. However, you need to remember that we are not going for an analytic approach here. We are going for a numerical approach. Therefore, we are going to generate these phis from the data. Oh, by the way, sorry, I forgot to define what phi is. Phi is just a collection of all your orthonormal basis functions. And turns out that these guys are what we call our orthogonal modes, so to speak. Right? We collect them into an array like this. So it's a tensor. And this procedure of expanding out ZH in terms of these orthogonal basis functions is called the proper orthogonal decomposition. For some of you, to give it a more physical perspective, these basis functions can be understood as the modes of the problem. That is, yeah, well, the modes. You can't get more physical than that, right? This is the crux of the proper orthogonal decomposition. We talk about how the dimensionality is reduced right now. I just give the equations numbers to make it easier to talk about. All right. Now we talk about the reduced model, that is reducing the dimensionality of the problem. As I've already mentioned, generating these high dimension solutions can be very expensive. These are the training data that we provide to the meta model, if you remember. And the meta model training data needs to be as accurate as possible. Therefore, we need a high dimension, high fidelity, extremely accurate solution. generating such solutions is very expensive, as we have seen in the previous slide already. So to obtain speed up, what we do is we try to reduce the dimensionality of the problem. The original dimensionality of the problem is n. So n could be, we shall see when implementing it, could be like 10,000 for instance. But we want to really bring it down to r. And we will see that r is something of the order of 10 or 11 or something ridiculously small like that. So this is what just blows my mind, that you can move a system from a 10,000 degree of freedom system down to a 10 degree of freedom system. It's just ridiculous. Anyway, let us call this reduced model as ZHR. The R superscript denotes that it is reduced. We, as usual, expand it in terms of its orthogonal modes as follows. The only difference being here that the summation does not go all the way up to n, but rather to a smaller number r, right? So it's basically just the first r orthogonal modes of the entire system. This can be expressed in convenient matrix form as phi r times alpha r, where alpha contains these scalar coefficients, phi r contains the reduced orthogonal basis. The goal of the proper orthogonal decomposition, which has at its heart the PCA, is to obtain this reduced basis such that an error is minimized. What is this error that we speak about? The error is, of course, when you reduce the dimension of the problem from ZH to ZHR, that is from a 10,000 dimensioned system to maybe a 10 dimensioned system, you are going to end up with some error or inaccuracies, that is guaranteed. The objective is to minimize this error as much as you can, right? So we need to develop or derive these basis functions numerically such that the error is minimized. The error is denoted by the L2 norm of ZH minus ZHR. The L2 norm, for those of you who are not familiar with function analysis, just refers to a Lebesgue 2 norm, which in my opinion is just a fancy way of talking about an infinite dimensional representation of your Euclidean norm. And even if Euclidean norms are not familiar to you, well, it's just the Pythagoras theorem in disguise, so don't worry about it. It's fancy terms everywhere. So we're minimizing the error. This is generally done in the least square sense, and you can use a set of optimization approaches to do this, like heuristics such as genetic algorithms, particle swarm fits, conjugate gradient, steepest descent, so on, right? And at the heart of this method, as I mentioned already, is the principal component analysis. And we've got a second method, which is very interesting, called the singular value decomposition. We speak about both these methods, and I will show you the advantages and the disadvantages of each of these guys in a bit. As we've already spoken about, both these methods require hi-fi or high fidelity solutions as inputs. In our terminology, we call this snapshots. A snapshot matrix is quite simple, really. It is basically a collection of high fidelity solutions. That is, we solve the high fidelity problem, that is the 10,000 dimension problem, m number of times, where m corresponds to the number of snapshots. For example, let's say we need 15 snapshots. This matrix would then be a 10,000 by 15 matrix. It's clear why, right? Because each solution is a 10,000 belongs to a 10,000 dimension space, and we arrange them in column form. So we get 10,000 by 1, 10,000 by 15, and this is a snapshot matrix. This is what we need to generate our orthogonal basis here, or our reduced basis, using either PCA or SPB. Now we speak about how the PCA is applied to this numerically generated data set right here. Again, equation numbers, just to make it easy. All right, the principal component analysis. This figure might be quite familiar to you already. The notion is that we have a coordinate system like this. We try to find a new coordinate system or a new space such that we can represent all the data, for example, in this way. This is a highly idealized representation. As you see, in the original configuration, we require 2 dimensions to represent this data. Whereas in reality, you could really just do with 1, right? Everything else is redundant. To express this mathematically speaking, the objective is to retain maximum variability of data. This is just a fancy way of saying that we want to find those specific directions where all the action is taking place, so to speak. All the data is in those dimensions. So you really want to find those. You want to eliminate redundant directions. To do this in a mathematical form, let us express each coefficient of the POD expansion in terms of ZH, like this. apologies for the slightly complex notation, but this is the best I could do really. So each coefficient of the expansion is expressed as a linear combination, and we have this psi I transpose times ZH over the entire finite dimensional space. As we mentioned, the objective is to retain maximum variability of the data, which means we want to maximize the variance. The variance of the matrix is calculated as follows. This is quite simple. I don't want to go into why this is the case. But basically, what you want to maximize is the variance over psi fi, which is the unknown that you're solving for. Here, psi I is your vectors of the expansion. CZH is the covariance matrix. This you might be familiar with. This is generated through the snapshot matrix that we spoke about. So it's the snapshot matrix transpose times the snapshot matrix. Of course, we need the bases to be orthogonal to each other, as we've already mentioned. That is the entire motivation of a proper orthogonal decomposition. Therefore, we impose an orthogonality constraint like this. So now this problem is a constrained optimization problem. And you might know what happens when you have constrained optimization problems. Of course, we write out a Lagrangian like this. The Lagrangian is in terms of the unknown psi I and lambda I. The first term here is the objective function we've got, and the second is the constraint incorporated. It's basically this guy incorporated here, right? And I'm sure you now see why this and this are equivalent. If you don't, you can refer to the notes again. Now that we've written out the Lagrangian, we need to find the optima. This is generally done by differentiating with respect to the design variable, which is psi I here, and we put this equal to 0. This is your standard maxima minima formulation, and we obtain as a stationary system the following thing. Now look, this is very interesting. We've got a matrix, that is the covariance matrix here. We've got our unknowns on an unknown vector psi I, which equals lambda I times psi I. If you remember the slide on eigenvalue decomposition, this is exactly an eigenvalue problem. All you need to do is solve for this eigenvalue problem, and it should be fine, right? Very straightforward. So we solve this eigenvalue problem, and the solutions we obtain for psi I are your proper orthogonal modes. Quite straightforward. Now we've had an entire series of proper orthogonal modes from 1 to n, but really all we need is the first R proper orthogonal modes. So let's say only the first 10 modes for the case of accuracy, right? That makes sense. Now, in the case of proper orthogonal modes here, via the principal component analysis, there are certain disadvantages. The first being that there are two bottlenecks in this procedure. The first one being computation of the covariance matrix. In reality, when dealing with high dimensional problems, you will notice that this can be a very expensive operation. That is, multiplying a 10,000 by 15 matrix by 10,000 by 15 matrix definitely takes some time, doesn't it? This is number one. Number two is doing the eigenvalue analysis for such a large problem can take a lot of time as well. Very expensive. So these are two small drawbacks of the principal component analysis. And the fact is, in reality, you don't really want all the orthogonal modes, do you? You just need the first R, and you should be good with that. So it's basically you're doing a lot of work for for too less gain, so to speak. So for this, to remedy this, we have another procedure called a singular value decomposition. This is nothing but, again, the principal component analysis in disguise. It's quite simple, really. It is an eigenvalue problem, but applied to rectangular matrices. If you remember, the snapshot matrix here is a rectangular matrix. It is not a square matrix. For this reason, you cannot do an eigenvalue decomposition on Z directly, right? Because the eigenvalue decompositions can only be done for symmetric or square matrices. Not symmetric, sorry, square matrices. In the case of rectangular matrices like this, we go for an alternative which is called the singular value decomposition. That is, we can break up matrix Z, that is the snapshot matrix, into three different matrices here. L is called the left matrix, which is an n by n orthonormal matrix containing the left singular vectors. This is by far one of the most important matrices for us. We shall see this in a second. R is the right matrix, which contains m by m orthonormal modes. This contains your right singular vectors, and psi is your n by n pseudo-diagonal matrix. I call this pseudo-diagonal because it is not a square matrix. A matrix can only be called truly diagonal if it is square, right? And the elements of the pivot are the singular values of Z. To form an sort of comparison between the SVD and the eigenvalue analysis, I would like to think of it this way. See, SVD or singular value decomposition is basically the eigenvalue decomposition for rectangular matrices. The matrix here, sigma, contains the eigenvalues, or in this case, the singular values. And the matrix L here contains your eigenvectors, or in this case, singular vectors. We just arrange this. Now, to obtain the orthogonal modes using the singular value decomposition, we arrange this in a decreasing order and sort through L and R accordingly as well. I don't prove this in this presentation, but it turns out that these terms here, sigma I squared, correspond to the modal energy along the oriented direction. So basically what we want to do is capture the first R important modes that contribute the most energy to the formulation. Right? That makes sense. As we mentioned, the first R columns of the reduced bases are your optimal reduced bases. Yeah, fair enough. This makes sense, I hope. Don't worry if it does not make sense just yet. I will implement them in, say, 10 minutes time, and it should make sense very soon. How do we choose the reduced dimension R now? Well, it's quite simple. We've got a formulation here, but I don't want to confuse you with this formulation. I would rather implement this live in front of you and show you what is happening. The notion is basically we set a truncation limit, and all the modal energies that fall above this truncation limit are the only ones that are accepted. We should see that in a minute. Don't worry about it. All right, and we come to the final slide of this section, which is applying this reduced order model to a real life system. We've got a real life dynamic mathematical equation here. This is nothing but your classical dynamic momentum balance equation for solid mechanics. This is your acceleration term, where this is your mass, this is your acceleration, this is a damping term, this is your damping coefficient or damping stiffness, so on. This is your velocities, this is the stiffness, and these are the displacements, Z of h, and this is a forcing vector. We are living in an n-dimension space, so this is an n by n system of linear equations. Right? Now let us talk about how to perform this dimensionality reduction procedure for this n by n system. If you remember already that we can express this ZH of R as a linear combination of the reduced bases, we write this in vector form as phi R times alpha. The alpha are the unknown coefficients. Phi R are the reduced bases that we have already computed using the SVD. So we approximate the ZH of R with this. The velocities are approximated similarly, phi of R alpha dot, and the accelerations are approximated as follows. Now we just plug it into this equation, and we will end up with an error, right? Because we're using a reduced basis, we will end up with some inaccuracies. Because we define this inaccuracy as a residual in computational mechanics, which is f of t minus the entire left-hand side. Now, to minimize this error or this residual, we need to ensure that it is orthogonal to the approximation subspace. This is called Galerkin orthogonality. This is to basically say that the influence of the error on the solution is minimal. This is just a standard trick in numerical methods. Whenever you want to minimize error, you enforce its orthogonality to the approximating subspace. This is what we do. And as a result, we end up with this, well, fancy looking equation. But in reality, it's not that fancy. Let's just take a look here. We've got phi transpose times m times phi. Let us write this in a reduced form here. This is interesting. Finally, from this equation on the top, we end up with this equation at the bottom. Do you notice something interesting? Here it is an n by n system, which is 10,000 by 10,000, ridiculously large. And now we end up with this, cute little equation, which is a 10 by 10 system. Very small and very easily solvable, right? Like I said, this is the full order model and this is the reduced order model. Once you solve this reduced order model at a reduced computational cost, you can recover the high fidelity solutions by basically just using these equations here. Finally, the full solution can be obtained from this guy, from equation 17, right? I know it looks like a lot of mathematics. Don't worry, we shall implement this in a second. All right, that's perfect. Now let us move on to something that is interesting, the applications and implementation. I have picked two examples that we implement here for your understanding so we can really get our hands wet. The first one is a simple example of a surface approximation in the time domain. There is a reason why I consider all these weird equations. I'll tell you in a second. We'll implement this live now. Given a surface which has this quite ugly looking form like this, you can see that it is a function of both the position and the time, as we've spoken about already. The position is a single dimensional case. It varies from 0 to 1. And we're talking about a system evolving from 0 to 2 seconds right here. This is how the system looks when it is simulated in its full dimensional form. What do I mean by a full dimensional form here? I just mean that it is a system that is solved at 25 points in displacement direction and 50 time points, which means you're living in a 50 times 25, which is 1250 dimensional space, right? Quite obvious. Now, let us see if we can compute the proper orthogonal decomposition, that is the reduced approximations to this surface at the moment. That is, we want to compute rank 1, 2, and 3. We want to reduce this 1250 dimensioned space to a space of 1 dimension, of 2 dimensions, of 3 dimensions, and see how accurate we can get this result. All right, so let us implement this. Let me open MATLAB right here. You can, of course, implement it on whatever you like. I just do it on MATLAB to make it easy for you. I keep this on the side here just for you to have a look at the equations. Let me move down. It looks like so far we have no questions. Okay, so here is the example. Let us go about implementing this guy. All right, quite simple. Let's just call it POD implementation. Of course, you can implement this on Python or C++ or whatever. It's just that I've just picked MATLAB because it's very simple to show, in my opinion. It's just my opinion, of course. All right. Now, we've got x varying from 0 to 1, right? And how many points have we got? We've got 25 sampled points. So let's create a 25 sampled point like this, ranging from 0 to 1. And we've got 25 samples, right? Very simple. So sampling x domain. Let's also in the same way create the time domain, which is link space or sampling time domain, something like this. This ranges from 0 to 2 seconds, right? Let me make sure. Yeah, 0 to 2 seconds. And we've got 15 time points here, all equally spaced. This function does this for me. It creates a linear space with these guys. Next, for the purpose of visualization, we need to create a grid. This is just a bunch of bookkeeping. Don't worry about it. We create a grid with all these points like this. So creating a grid. It's simple. Now we define this function here, right? This fancy looking function. It is z equals exponential of minus absolute x 0.5. Yeah, x minus 0.5, apologies. Like this. Times time minus 1, of course. And you create a bunch of brackets to close everything. Make sure everything's closed. Close looks good. Plus the sign of x dot t. So what we're doing is generating z. Fair enough? Just make sure it is correct. Yeah, it is correct. Okay. Next, we can just have a look at what this looks like at the moment. It is x, t, z, the surface. Right? Let's have a look at what the surface looks like at the moment. What's the trouble? Okay, dimensions. Oh well, don't worry. Just make sure it is proper. And where is the figure? Let me just get the figure out. Apologies. Let's run this again. Here we go. So this is the complete figure that has been generated. So make sure, let me see if I have any questions here. Oh, no questions. Okay. We have this complete figure here. Now let us begin with doing the reduced basis approximation. Just to give it a good label, let us call this, give it some labels here, right? And make sure all the figures are closed at the beginning. Now running this, we get the actual surface here. This is the complete actual surface. Let us see if we can approximate this using a reduced basis form. First, let us talk about the singular value decomposition that is being performed. Let me navigate to the singular value decomposition equation here, basically equation 40. This is what we're doing at the moment. So you've got three matrices, U, S, and V. These correspond to L, sigma, and R. Don't worry about it. MATLAB has a nice function called singular SVD, singular value decomposition. Let me just go ahead and singular value decomposition. Equation 40. Perfect. All right. So we've computed this. Now let us do it for 3 ranks. Remember, in the problem, we are doing rank 1, 2, and 3 approximations, right? So let us compute this for k equals 1 to 3 for rank 1, 2, and 3 approximations. Perfect. Let us compute these approximations. So let us say the Z reduced is, we only need the first k eigenvectors or singular vectors in this case, right? This makes sense. Times we only need the first k singular values. So single ranked problem, we just need the first eigenvalue, first singular value. Times, sorry about that. Something like this. And remember, this needs to be transposed. This is again equation 14 approximation. Okay, for those of you who are not familiar with equation 14, this is the equation. Quite simple stuff. Let us plot all these approximations here. Well, let's do it like this. Visualize the reduced basis approximations. All right, perfect. And just to make it readable, let us give it some labels and titles as well. Let's know what's going on. All right, very good. Let's run this and have a look. All right, we don't have anything. We can fix it, no problem. Here we go. Here we are. Right. This is interesting now. This is the actual surface that we've got. We've got a rank 1 approximation here, and then we've got a rank 2 approximation and a rank 3 approximation. Can you see that maybe there is a difference between rank 1 and the actual surface? That is, the actual surface lives in a 1250 dimensional space. We've reduced it to a single dimension here. You can see that there are some inaccuracies, aren't there? Well, there are. Just have a look at it. For rank 2 also, it's much closer to the actual surface. That is, now we are working in a 2-dimensional space as opposed to a 1250 dimension space. Here also you can see a few discrepancies. However, let's have a look at rank 3. You can see that this and this are virtually identical, right? I think so. Well, it does look identical. So this is good enough for us. What you have noticed now is that we've brought down the problem from a 1250 dimension space to a 3-dimension space, and it works just as fine. Isn't that cool? That's really cool, I think. All right. What do we need to do other than this? Oh, yeah, we need to look at a couple more statistics to see what's going on. Let us look at what the singular values look like. This is classically called the singular value decay problem. Plot singular value decay, something like this. So to do this, we extract the diagonal components of S, and we do a log plot, that is a semi-log plot of these guys. So something like this. All right. And just to make it clear, let us give it a title. There is what title shall we give it? Let's give it this title. Yeah. Let's run this. Let's have a look at the singular values now. Oh, we don't have it. No worries. Well, we will have a look at it in a moment. Or shall we just have a look at it now? No, we'll just have a look at it now. Well, it's not up here. Here we go. That's the trouble. All right. So these are the singular values of the problem. This is interesting. This will give us a lot of insight into the problem. It basically tells us that the first singular value here gives us the maximum energy. That is, it gives us an energy of a little over 10 power 1. It's a fraction, basically. Then orthogonal modes or singular values 2 and 3 are equivalent. And from 4 onwards, you can see it decays, and maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. From 14 onwards, you can see it really doesn't matter. So in my opinion, with the first few singular values, you should be able to approximate the problem quite well. And yes, you have evidence for this, right? So yeah, that makes sense, I hope. What else do we need to plot? Oh yeah, finally, let us also plot the contribution of each orthogonal mode to this problem, right? So to do this, first let us create a new plot, subplot, maybe 3.2.6, something like this. And let us only take the first 3 eigenmodes, or first 3 orthogonal modes. Let us take only first 3 orthogonal modes, right? Like this. Now, using equation 17, we compute the full solution. That is, here C equals, C is in this case the full solution, is V transpose times Z transpose, which is equation 17. Alright, perfect. Now let us plot these modal coordinates. I'll just copy and paste from the graph I already have, just to make it quicker. Don't worry about it. And as usual, give it some labels. Something like this. Very simple. Now let us run this and see what we have. Interesting. All right. Let us have a look at the final picture here. This shows us the modal contributions of the problem. All right. As you can see, the first mode here is the one that seems to be, well, it seems to be contributing the most. The other two seem to be irrelevant. This is all I wanted to show you here, really. All right. That looks good. Now let us move back to the presentation. This was an example of a simple implementation that we have, right? I've tabulated these results here for you. We can discuss this further if necessary. So this is the actual surface. We've got a rank 1 approximation, a rank 2 approximation, and a 3. This is the singular value decay as we've just seen, and the modal contributions, right? So it's all perfect. Now let us move on to another dynamic example, which is a little more complicated. This is a real world problem. It is basically my PhD topic, so to speak. It is the acoustics of porous media. We'll very quickly talk about the mathematics involved and then move on further. This is an example of a two-phase problem. That is, we've got a solid skeleton U and a pore fluid P, something like this. The kind of example we're going to look at now is that the porous material is placed inside an impedance tube or a Kunz tube configuration like this. This is standard acoustic stuff. We subject it to acoustic excitement like this and study its behavior. These are the partial differential equations, that is the mechanical model equations that govern the physical phenomena. These are based on physics. These are your classical momentum balance equations in the solid phase and the fluid phase. I don't want to go too much into the mathematics here as it is not directly relevant to our conversation right now. The way we solve these equations is, by the way, using finite elements. This is known as the strong form, which is we've got a coupled partial differential equation in the frequency domain, and we move this into an integral form, and we achieve this set of linear equations here. Don't worry if it looks very scary, it is not very relevant. I just show you the equations here to be complete. And anyway, we'll be solving this in a second live, so you can see what's happening. The interesting thing is now we've broken down the partial differential equation using numerical techniques into a series of linear algebraic equations like this in terms of displacements and pressures. All right. Yeah, well, quite straightforward stuff. We've got K, M, C, and Q. These are different matrices. They ultimately look like your standard matrices, that is a square matrix, symmetric in nature and so on. And these are complex value parameters, and they're solved over an entire frequency domain. All right, I just wanted to get past the mathematics quickly. Let us go into the implementation for this guy to see what's happening. Let me keep the theory open over here for you to have a look at. Right, here is the theory. Let us implement this. It will take some time, but it will be worth it, I'm sure. All right, so this is a finite element model. Let us define the size of our problem here, head sample. Let's call it 80 millimeters. Define it as problem control. So this is the size of the domain under consideration. Since it's a finite element model, we need to specify the discretization. So let us call it maybe 50 by 50. You've got 2,500 elements. And let us create a domain like this. So the domain proceeds from hex sample, something like this. And well, we've got the same for the y direction as well. So we've modeled a square domain here, which ranges from 0 to x sample, which is 0 to 80 millimeters. Now we create a mesh for this guy, that is a quadrilateral mesh over which we solve the entire discretized problem. For the quadrilateral mesh, we need the coordinates, we need the connectivity, we need the boundary nodes to specify constraints. This equals create quadrilateral mesh. These are functions that I already have, so don't worry about how these functions are implemented. Just treat them as a black box for now. Right. So x length, y length, and the number of elements. Let's run this and see what we've got so far. And well, we don't have anything. Of course, we shouldn't have anything. It is making sure that it all works. Close all, clear all, CS. Just to make sure it's all good. Does it work so far? Yes, it does. Okay, perfect. So now we have a mesh. Next, what do? We compute the number of nodes that this mesh has. So this gives us the number of nodes. Mesh something like this. If we run this result, we should see how many nodes this problem has. This problem is solved over a mesh containing 2,601 nodes. And as I mentioned, this is a displacement pressure problem. We are solving it in two-dimensional physical space. That means we've got 2 displacement degrees of freedom and 1 pressure degree of freedom per node. Therefore, we've got 3 degrees of freedom per node, which means we've got 2601 times 3. We are living in a 7,803 dimensional space at the moment. This corresponds to a high fidelity model, and we will see how to reduce the dimension of this model very soon. Just for our purposes, we'll create a display function here to tell us what is going on. Now we create a finite element matrices. So let's create finite element matrices. These correspond to these guys, K, M, W, H, C, so on, right? All right, so I'm not going to dwell too long on this because this is not the topic of this talk. These are just numerical methods. I just implement them very quickly for you. Let's see, we've got matrices K, M, H, Q, C, and C transpose. So allocate memory for each of these guys. So we allocate memory. We solve this problem over a frequency spectrum, right? So let's give it a frequency spectrum ranging from minimum 20 Hertz to maximum 5,000 Hertz. And the number of frequency steps we're solving it over, let us say it is 100. And let us create a list of frequencies now. Fmin, Fmax, Fmax. Creating a list of frequencies. Right spelling, never mind. Now, first, we need to create a snapshot matrix, if you remember. What is the snapshot matrix? Let me move back here. This Z here. We need to create this guy, the snapshot matrix. Snapshot matrix is generated using high fidelity models, right? So let us create this. Let us initialize this first. So zeros of. Remember, we've got 3 degrees of freedom per node. So let us initialize it as follows. and we solve over n frequency steps. So we've got this kind of a matrix. So we pre-allocate memory for full order model, also known as FOM or form. For purposes of visualization, we will also create arrays for the x displacement, y displacement, and z and pressures like this. Create this for x, this y, and well, let's create it for pressure as well. This will be for pressures, right? This is creating a U displacement and pressure matrices. It's simple. Finally, let's move on. Let's keep a timer here just to see how long the full model takes us. So we put in a tick and we loop through each frequency. So looping through each frequency. So this is generating the snapshot matrix for a full order model. I've already have a pre-programmed finite elements solver, so don't worry about how the partial differential equations are solved. It is not important for us. What is important for us is what we do with the model once we have the snapshots. So don't worry about these guys. I just put this in. We have a finite element vibroacoustic solver here that I've already pre-programmed. It requires as an input the mesh, the frequencies that we are solving over, this guy here, and the pre-allocated matrices K, N, H, Q, C, C transpose. What we are essentially doing here is solving equation 24. Just solving F24. Right? Quite straightforward stuff. Of course, this is a constrained PDE, spatially constrained. We assign it some boundary conditions here. Don't worry, it's not too important what this happens. I just do it to be complete. So here we assign pressure boundary conditions, boundary excitation, I should say. And finally, we solve the problem. Solving the problem basically says that we're solving for U and P, that is, we're inverting this matrix to solve only for the unconstrained dimensions like this equals Z, 3 dots, 3 dots over F. Perfect. So solving the full order model. Alright. So far, everything looks good. Finally, we're not done just yet. To verify that this model is correct, we generally use certain acoustic indicators. Don't worry about what these indicators are, it is just to verify the solution. So we do this in post-processing. I've already written a function for this. Don't worry about it. What we do is we extract an acoustic indicator. This is called a sound absorption coefficient. We've got displacements, pressures, and so on. Right? Now let us do this and solve the full order model. Like this. And that is it. That is our full order model. Let us solve this and see how long it takes. While it is being solved, let us meanwhile construct a reduced order model for dimensionality reduction. Alright. So the first job is to extract the snapshot matrix from the full model. Right? As you've seen, we need to create matrix Z. Where is matrix Z? Here we are, matrix Z. Let us say the number of samples, number of snapshots we need is 15, for example. So this number of snapshots. So what are these snapshots that means? Let us randomly sample these snapshots from the list of frequencies that we've already got. MATLAB allows you to do this through the following function. Replace. Also. This just means that you are generating independently, identically distributed data. Don't worry about the kind of distribution you're sampling it from. It could be Gaussian or anything, chi-square distributions if you like. It's not important. So what we're doing is pseudo-random sampling from frequencies. Alright, let us have a look. Oh, by the way, it looks like the thing is done. It took us 27 seconds to solve the full order model. Right? Now, by running this section, you can have a look. Oh, apologies. This should work now. Have a look at the sample frequencies. You can see that we've randomly sampled a set of frequencies like this from the list that we already have. Right? Moving on. Let's make a list of all the frequencies that we have not sampled so far. So there's the remaining frequencies. Let us basically do a difference, a set difference. Just check the sample checks. Right? This will give us all the frequencies which we have not sampled. Now we need to pre-allocate memory for the snapshot matrix like this. We got 3 decoms per node, as always. Initializing the snapshot matrix. Quite simple stuff. We also want to solve the reduced order model, so let us allocate memory for that as well. Again, very standard stuff. New here. Exactly as we have already done it for the full order model. So let us again create displacement vectors for each of these guys. We've got ux, y, p, u1, and p here. Displacement measures for reduced order model. Of course, if you like, we can make this code available to you, no worries. We want to look at how long this takes, and we begin solving the reduced order model. First, we begin solving the reduced order model, right? So first, what we do is we need to generate our orthogonal basis. Generate proper orthogonal basis, also known as reduced basis. That makes sense. I hope it does. So let us run through a number of samples. I think it's supposed to be like this. Perfect. Now what we need to do is solve the problem over each of these domains. Once again, let us solve the finite element model as before. Just copy paste it to save time. Solve the finite element model over these snapshots, and we assign the pressure, excitation, the boundary conditions as before. So to the snapshot matrix, the pressure, DC, DOFs come on like equals 1. So we just got a unit pressure excitation. Something like this, and we solve the snapshot model. DOFs come out like equals Z. Again, only solved for the unconstrained degrees of freedom like this. If anybody has a question as to what the backslash operator is, we can discuss this further. It's just a MATLAB solution procedure. So we're obtaining the high-fi snapshots over here. Right? This makes sense. That is, we're solving the complete full order model over these problems. And let us post-process the solution as we did before to get certain acoustic indicators, things like this. Don't worry about this part. It's not very important. Now that we've done this, let us save the snapshots in the reduced order model. Right? This makes sense, I hope. Equals snapshot. That is, we save the snapshots in reduced order model solution procedure. Quite simple stuff. Now we have the snapshot matrix, right? So we have generate snapshot matrix. With this procedure, the snapshot matrix is done. The next is to generate the singular value decomposition. Again, as we've already done this, quite simple. We only need the left and the singular vectors. We don't need the right, actually. Right? You do SPD of the snapshot matrix as before. This 0 is the second argument we add here. This is basically telling MATLAB that we can do an economical SPD, because SPD can be quite an expensive operation if not done efficiently. This just tells MATLAB that, calm down, we don't need all the singular values, we just need a few. So what we then need is obtain the singular values from the diagonal matrix here, like this. forming a list of diagonal singular values. We create an error tolerance. This tells us the desired accuracy that we're looking for. So let's say we want a reasonably accurate solution. We give it an accuracy of 1e minus 16, that is 10 to the power minus 16, which is ridiculously accurate, of course. So this should be our desired accuracy. Now let us go about truncating the model. In the previous example, we manually decided that, okay, we want a single rank, a 2-rank matrix, a 3-rank matrix, and so on. Here we are going to not do that assumption. We're going to let the computer decide for us what the reduced model should look like. So let us truncate it. What we're going to do is find the ratio of the energies. That is what it, so let me just make it in another line here. Energies equals, or maybe I should call it relative energies. That would be better, right? Singular value squared divided by maximum singular value squared, which will give us the relative energies. Now, we make sure that we are only extracting the modes or the proper orthogonal modes which are of the highest energy. So, energies, make sure that these guys are above the error tolerance that we need. Right? This is all we did. So, what we're doing is truncating singular values or extracting only high energy orthogonal modes. Something like this. With this, we have finished the singular value decomposition. Finally, we construct a POD reduced basis. By this, I just mean you need to truncate the left singular vectors as well. Let's call this something like this. 1 to length of truncated singular values. This is truncating the left singular vector to obtain reduced basis. It's just that simple. Do you see how simple this is? Very nice. Finally, now we are done with the reduced basis. Right? All we need to do now is solve the reduced order model over remaining frequencies. So we solve it over only the remaining frequencies because we don't need to solve it over the sample frequencies. We already have the high-five snapshots for that, right? Why would we solve it again? Remaining frequencies like this. Follow. Once again, we solve the finite element model over this guy. I'm just going to copy paste to save us time. We solve the reduced model here. Excuse me. So, okay, this is the important step, the Galerkin orthogonality. Let me just move here. Make this equation open for us. Here we are. I needed to pay attention to equation 19. This is what I'm going to be implementing right now. So, reduced model Z ROM equals V 3 DOFs. The V corresponds to our orthogonal basis. Transpose times Z. Look familiar to you, right? Z 3 DOFs dot V. Apologies. 3 DOFs. Quite straightforward. We do the same thing for F as well. So F reduced order model equals V 3 DOFs, comma all. This into F 3 DOFs. Very simple. So we have again X19 opposing Galerkin orthogonality. Quite simple, very standard stuff. Now these are our reduced models, and we solve for the reduced dimension problem like this: Z ROM over F ROM. Solving the reduced order model, so like this, and we assign it to the appropriate space. Frequencies. Alpha equals V times solve. We recover the high fidelity solution That is equation 17. Right? We're basically talking about this guy right here. Quite standard stuff. Once again, we do the post-processing to enable certain comparisons. Don't worry about this, I just copy-paste it. And finally, the solution procedure is over. So we record how much time this entire procedure took. And we display these guys for our viewing pleasure. So to save time. Right? We display this and well, we're done. Let's run this. Hopefully I haven't made any errors during programming. If you have, don't worry. Meanwhile, while this runs, I would also like to do some comparisons. So I just add a plotting routine which I developed. This will just visualize a bunch of results for us. All right, don't worry about it. It will take a few seconds. Let us see what happens. We can obtain some statistics on this now. Meanwhile, does anybody have any questions or nobody has any questions? Unable to perform. Okay, looks like I made some bug. Don't worry, we can fix it by doing this. Again. This is the trouble with live coding, right? You always make some trouble here or there. But don't worry, I'm prepared for such eventualities.
Abhilash, there are a couple of questions on the chat.
Oh, are there? I don't notice this. Oh, apologies. When you say tensor, so I'm really sorry for not seeing your questions. I see it now. When you say tensor, is it, for example, pressure or multidimensional matrix? Well, I'm not sure which tensor you are referring to, but yes, when I say tensor, I just mean a matrix, anything like this. So for example, this is a tensor. This guy here is a tensor. Tensor and matrices are interchangeable for me, mathematically speaking. Hope that answers your question. So when would one prefer to use SVD over PCA? That's a good question as well. The reason why I prefer using SVD over PCA is the disadvantage that I mentioned for you right here, which is, let me navigate here. Can't seem to find it. Here we go. In the PCA, we've got to compute the covariance matrix, we need to compute basically equation 10 over here, right? This, in the case, for example, let us consider this problem which we've solved here. This Z matrix is a 7,000, something like this, right? It's a 7,803 dimensional matrix times of 15, right? This is the size of the tensor or the matrix we're trying to multiply. This can take quite a bit of time when applied to equation 10 because it's a large matrix, number one. Number two, doing the eigenvalue decomposition for such a large system takes time. You can try this out yourself. I'm not doing it here, but you can try it out yourself. Right? It takes quite a bit of time. Very expensive. And for these reasons, I would prefer to go with an SVD when the problem size becomes genuinely large. The only trouble with the SVD is that at the moment, it's a bit of a black box. I do not explain exactly how the SVD is happening. So the thing is, you don't really know what's going on inside. You have to trust the algorithm, but it is faster. The PCA, on the other hand, you know exactly what is going on, but it takes a little bit of time. So to answer your question in a short way, I would go for the PCA only when I want clarity on the method. SVD generally speeds up things. All right, that answers your question. All right. While speaking about this, I decided to solve the problem again, just to really show you what is going on a little better. Just give me a couple of seconds, it should be done. And are there any more questions? No. I hope this makes sense so far.
Yeah.
Okay, thank you. Now, let this be solved fully. Just give it a couple of seconds. I'll just drink my coffee meanwhile. Oh, it's done. Oh, wow. Do you see these results right here? Isn't that amazing? The full order model took us 50 seconds. The reduced order model took us 1/5 of that time, 10 seconds. Of course, you will see that there are some caveats with the inaccuracies, but let us compute how much time we saved in this. So we got 51.7332 minus 10.8103 divided by 51.7332 times 100. Wow, so we've got a speed up of nearly 80% using the reduced order model. Isn't that amazing? This is brilliant to me. And that is number one. Number two is that we'll see this in a second. Let's have a look at the pressure and displacement contours here. Let's look at the pressure contours first. The first guy over here is the solution we obtained for a full order model. That is for the 7,803 dimensional space. This is what it looks like. Now the second column is what is interesting for us. This is the solution we obtained from just solving a 10 degree of freedom system over a 10 dimensional space instead of a 7,803 dimensional space. And you can see how exact the results are. I'm sure you cannot spot any difference. Isn't that amazing? Now we solved, let us say, just to show how inaccurate a system could be without the reduced order model. Let us try to solve the same problem over a low-fi system. That is, in this case, I just solved the sort of full order model over only a 12-dimension space. And you can see how inaccurate it is compared to the full order model. By this, all I mean to say is that the reduced order model is much more accurate than a full order model, even though they have more DOFs here. We got 12 here, we got 10 here. Yet you can see that our proper orthogonal decomposition is giving us nearly the exact answer in 80%, like 1/5 the time. We're saving 80%, which is just brilliant to me. You can see the same behavior in the pressure contours as well. Let me open the pressure contours. Once again, the reduced order model is nearly exact as the full order model, isn't it? You can barely spot a difference. Whereas the so-called low fidelity model here is terrible. It gives us a rubbish solution compared to this. Isn't that brilliant? And turns out the reduced order model is just as quick as the low-fi one. And it's 1/5 the time it takes to do this. Once again, this shows the benefit. Another important observation here is this. This is a useful acoustic indicator we use called the sound absorption coefficient. Don't worry about what it means, but it's a measure of how much energy is absorbed by the system. All right. Now I've got a couple of solutions plotted here. The reference solution is something called the TMM, that is a transfer matrix method. Don't worry about what it is. We just use this in acoustics as a sort of reference, exact God solution. We compare the full order model, and you can see that the absorption coefficient seems to be exact across all frequencies, nearly exact. Now, interestingly, even the reduced order model, that is, we solve it over 10 degrees of freedom instead of 7,803, we see we get the near exact solution. On the other hand, this low fidelity model, we solve it over 12 degrees of freedom, which is even more expensive. But turns out, look, it gives us a reasonably accurate response up till maybe, say, 2000 hertz. After that, the solution just falls. It just becomes rubbish, right? This is a well-known phenomena in computational mechanics. That is, it is difficult to solve high-frequency problems for very obvious reasons. We can talk about that later if we have time. And that is exactly what we're observing here. That is, in the low frequencies, it seems that even we can get away with using a low-fi model. But in high frequencies, we absolutely need a high dimensional space, or in this case, even the reduced space is sufficient. That's pretty cool to me. Now, finally, let us look at some of the analytics of this method. We've got the singular value decomposition. Like if you remember, we took, how many singular values did we take? We took only 10 singular values. Let's look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've taken only the first 10 singular values, and this has helped us reduce the dimension from 7,803 to just 10. This is because we've given it an accuracy, if you remember, of 1e minus 16, correct? This is telling us that we don't want these lower order energy modes because they just don't contribute much to the formulation. It's only the first 10 guys that really contribute. So with this, we can see that we have reduced the dimension of the problem from 7,803 to 10. How many degrees of freedom have we saved here? 7,803 minus 10 divided by 7,803 times 100. Wow, we've got a 99.87% reduction in the complexity. Isn't that amazing? And we've saved how much? We've saved 80% of computational time. And this is just for a single problem. Remember the original problem where we had to simulate over 1,000 different cases. So imagine just how much time we would be saving. Let us say, for argument's sake, one simulation takes 60 seconds. 1,000 simulations would take 60,000 seconds, which is how much? It is 16 hours, right? This is the full order problem. And if we use the reduced order problem instead, how much? We save 80%, right? So we only use 0.2. Instead of 16 hours, we're able to solve the problem within 3 hours. It's just brilliant to me. And the scaling just goes out off the charts. So it's really cool, right? All right. I was a little too enthusiastic there. Apologies. Let me come back to the presentation. Here. Very quickly, don't worry, we're reaching the end. Already mentioned this. But let me get my laser pointer out again. So these are just the results that we have simulated here. I put them in the slide for you just to discuss what's going on. Let us summarize all that we have seen in this example. The full order model, we solve it over 50 times 50, that is over 2,500 quadrilateral elements using the finite element method, and we've got 7,803 degrees of freedom. The reduced order model has got only 10 degrees of freedom, as we've seen. The low-fi model is solved over a single quadrilateral element, that is 12 degrees of freedom. As we mentioned already, the reference is a semi-analytic solution computed through something called the transfer matrix method. It's not very important. And we've seen that we've computed the problem over 20 to 5,000 hertz and 100 frequency steps. The sound absorption curve, as I've already mentioned, is the measure of acoustic energy or acoustic power absorbed. Before that, the result here, I've already discussed this. The full order and reduced order model are both nearly exact when compared to the reference solution, but the low-fi model only offers reasonable comparison at low frequencies as expected. As we go into the high frequency territory, it gives us inaccurate results, which is not good. This is the singular value decay chart, so to speak. For a desired accuracy of 10 power minus 16, it turns out we end up with 10 truncated singular values, and therefore the dimension of our reduced space is 10. What else can we get from this? Yeah, I mean, this is already what I've spoken about: form, ROM, TEM, TMM, identical, low-fi, yeah, all basic stuff. I've also mentioned the displacement and pressure contours here. And these are the contours at 500 hertz. I put them at the highest frequency because I want to show you the results at the most difficult frequency to simulate. As we've already seen, the low-fi model contours are noticeably inaccurate when compared to the reference high order models or full order models. The ROM contours are practically identical to the full order models, right? Oh, well, when I simulated the results yesterday, I only achieved a 72.31% speed up, but today it looks like we've achieved a near 80% speed up. So it really depends on your computational environment. All right, I have not shown you this result here, but it's just what happens if I push the problem even further. We ran the problem over 50, 100, 500, and 1,000 frequency steps, and we see the amount of time we save here. We've got a significant reduction and a speed up of near up to 266.7% is seen, which is just, I don't know, off the charts for me, you know. And we've got 1,000 frequency steps, 500 frequency steps, and so on. Now, what else can we get from these charts? We see that the time steps is this, and the frequency steps are, we solve it over 50, 100, 500, and 1,000. And yeah, well, we see a significant this thing. Now, one important thing to notice here is that we've got at the low left side, that is on the left here. Oh, sorry, I see a result here. Hi, Abhilash. Your results are amazing. Why high frequencies are a problem with low-fi models? Oh, okay. That's a good question. Let me just move back here. This is the question is, why are high frequencies a problem with low-fi models? The reason is very simple. Well, we need to look at it from a physical perspective. High frequencies basically mean you're talking about low or small wavelengths, right? An acoustic wave which is moving at a high frequency means it's small wavelength. Therefore, you require a mesh discretization that is small enough to correctly resolve these waves. So if you have a large mesh, it is equivalent to saying that you're missing out these small waves. So when you're having like wavelengths of the order of 1e minus 9, 10 power minus 9 of the nanometer range, you need meshes also that are small enough to capture these oscillations. So this is why I say that low-fi models, that is coarse meshes or low discretization meshes, are unable to capture high frequency results. Does that answer your question? I hope it does, I wonder. All right, so look at this. The only caveat here is that it is probably a good idea to go with the full order model when you have a low DOF system to begin with in the first place, right? Because you can see here at the bottom, they're both equivalent. And in fact, I can tell you that the full order model outperforms the reduced order model at low DOFs. So caveat is you only want to run this reduced order model when your dimensions are huge. Finally, we are up to the limitations here. So far you must have seen that this seems like, black magic or what, or witchcraft, right? At least it seemed to me. The fact that you could reduce such a huge problem to such a small problem and still recover such accurate results without compromise just blows my mind anyway. However, like I said, there is no free lunch. There are some issues. We'll talk about what the issues are here. Number one, manifold complexity. That is, we need to know about something called the Kolmogorov width. This is the N width. It is a measure of the parametric manifold complexity. An example is, this is an example of a low Kolmogorov width. By this, I mean that the domain we are considering is generally homogeneous in nature. That is, the parameters don't vary too crazily. An example of a high Kolmogorov width is when the parameters are also quite chaotic, as in the second picture here. This is an example of a highly heterogeneous parameter distribution. In this case, in fact, I can tell you that the POD reduced order model will not work very well. It will work well here, it won't work well here. Why is that? The reason is, with low parameter or Kolmogorov width manifolds, a single reduced basis is sufficient. It is globally optimal. That is, if we are able to come up with a single proper orthogonal basis, it can accurately span this entire domain. Whereas in the case of a chaotic guy like this, that is often not the case. In high Kolmogorov width manifolds, a single reduced basis is insufficient. You need to think of, for example, plates versus shells. For mechanical engineers, plates are a flat domain where it is sufficient if we have a single basis to span the entire thing. Whereas a shell is more of a curved domain, so you are in curved space. Because of this, you need a basis that varies along the curve itself, right? This is basic geodesics differential geometry. In this case, as I mentioned, you need multiple locally optimal reduced bases to be evaluated. For handling such problems with high Kolmogorov width, you require more sophisticated methods, such as a hierarchical proper orthogonal decomposition with enrichment. Right? Apologies. I hope I didn't get cut out right there. Hope it's all good. Anyway, requires more sophisticated methods such as a hierarchical POD with enrichment. That is, you locate certain tiny spots and you refine them further. Or some other options such as domain decomposition. That is, you partition the entire domain into small segments and you find reduced bases over these guys. And certain other techniques borrowed from differential geometry, such as the notions that we use in general relativity, shells, and so on. Another limitation that this method has is that cannot be applied to nonlinear data. PCA derived algorithms only work for linear stuff. I think any of you from a machine learning background already know this, right? So something like this would work just fine. But what happens when you have nonlinear data, something like this? A PCA will not work. You can try this out, but I can guarantee you that it will not work. Why is this? This is because the neighborhood is not conserved during the projection onto the reduced subspace. Now, of course, there exist several alternate methods, such as the absolutely amazing locally linear embedding technique. This is basically an unsupervised technique, which is like a competitor for clustering, where you map the points onto the reduced domain while preserving the neighborhood. There is a nice paper for this. If anybody's interested, I can give this to them. Kernel principal component analysis. This is nothing but PCA, but combined with a kernel trick. That is, you map the entire problem onto a high dimensional space where you can linearly separate the data, and then you apply the PCA there. Nothing too fancy. To be honest, I'm not too sure what a t-distributed stochastic neighbor embedding is. All I know is that we sample points from a t distribution, but I cannot tell you more about this, unfortunately. And we've got another variant to the principal component analysis here, which also helps to solve this problem. This is a nice figure where it just shows you what is happening in the neighborhood preserving a local linear embedding algorithm. Even for a non-linear manifold like this, you can, using this algorithm, map it accurately onto a reduced dimension space here. Here, it turns out it's a two-dimensional space. Cool. Those are two of the many major limitations of the method. Finally, we are on to our final slide now. But don't worry about these pictures. These are just some pretty pictures I generated just to make the slide look nice. Anyway, to summarize what we've looked at all today, data-driven models, they require large, hi-fi, finite element generated training data. This proves very expensive, as we've seen. The POD, that is the proper orthogonal decomposition, is a powerful tool to accelerate offline training. As we've seen, we reduce the time for data generation by nearly 80%, which is amazing. The heart of the POD is the principal component analysis and the singular value decomposition. Right. Just to clarify, I hope my screen is visible. Please, one of you let me know if any trouble is there. The heart of the POD is the principal component analysis and singular value decomposition, right, as we've seen. The manifolds that we've looked at so far are created by spanning using a reduced basis, either with principal components or singular values, right? Very simple. The dimension of the manifold is the same as the modal expansion, which is truncated. And as we have seen, this affects the solution accuracy. In the first example, remember, when we had a rank 1 approximation, there were certain inaccuracies. But when we had a rank 3 approximations, it was way more accurate. This is something I haven't talked about, but it is difficult to know a priori the correct reduced dimension. It looks like in the presentation which I showed you right now, I knew everything, it all worked perfectly. But to tell you the truth, there was quite a bit of experimentation in the background. For example, how did I know that we only need 15 singular values or 15 snapshots or 10 singular values, so on? It was just through trial and error that I determined this. I'm not sure if there exists any a priori error convergence results for this. Maybe there does, but I haven't seen it. And as a final caveat or notice, you cannot use this with highly heterogeneous or non-linear parametric space. Perfect. Now, just to conclude this presentation, these are some of the publications I referred to. If anybody likes to, they can have a look at these guys here. Right? If anybody is further interested in this, I would recommend checking out these three guys. These guys are really well known in the field of data-driven modeling in physics and mechanics. And yeah, you should really check out their work. It's really amazing. Okay, and with this, I come to the end of my presentation. Thank you, everyone. I hope it was not too intimidating. Tried my best to make it useful. Don't worry, if you have any further questions, we can always discuss this further. If you would like some code, if you would like anything, please feel free to ask. Even if you don't have questions at the moment, we can discuss this anytime. You know where to find me. Thank you.